Well, the arrival of quantum computers could be even more historic than that. We are now witnessing the dawn of yet another monumental shift in human history, the early phase of a groundbreaking revolution. A somber cloud fell over the scientific world when an advanced quantum computing system, hailed as a game-changer, had to be unexpectedly deactivated due to critical emergency concerns. Amplifying the mystery, world-renowned theoretical physicist Michio Kaku, in a stunning and unsettling interview, disclosed alarming truths about the trajectory of quantum computing. He didn't stop there. Kaku also unveiled astonishing revelations involving extraterrestrial intelligence and artificial consciousness, insights that reverberated through the global scientific landscape like a thunderclap. What caused the immediate shutdown of this powerful quantum machine, and what jaw-dropping information has Michio Kaku brought into the public eye this time? Stay tuned as we delve into this emotional moment, where Kaku is visibly shaken and moved to tears after a quantum computing system was brought to an abrupt halt. Throughout the 21st century, a cascade of radical innovations has reshaped the very fabric of our civilization, redefined industries, and granted humanity capabilities that once belonged to the realm of science fiction. From the astonishing rise of artificial intelligence to the mysterious world of quantum computation, this era has delivered one revolutionary breakthrough after another. Among these trailblazing technologies, quantum computing stands out as a particularly promising and transformative field. Initially dismissed as a speculative theory conceived by a few ambitious scientists, quantum computing has now evolved into a deeply sophisticated technology capable of achieving feats previously deemed impossible. The seeds of this transformation were planted in the early 1900s with the emergence of quantum theory, a revolutionary concept in physics that unraveled the enigmatic behavior of atomic and subatomic particles. This theory laid the foundation for what would eventually become quantum mechanics and ultimately led to the theoretical underpinning of quantum computing. However, the notion of harnessing quantum mechanics for computation didn't gain significant traction until 1980, when visionary scientist Paul Benioff proposed a bold new direction, utilizing the principles of quantum physics to design a new class of computational devices. He suggested that quantum systems, which harness phenomena such as superposition and entanglement, could be repurposed for computational tasks in ways that defied the capabilities of traditional digital machines. Benioff's provocative idea was soon taken further by physicist Richard Feynman, who, in 1982, presented a compelling vision of computers built entirely on quantum mechanical principles. Feynman believed that such machines would not merely enhance existing technologies, but could tackle computational problems so complex that conventional computers would be rendered obsolete in comparison. Though radical at the time, his concept sparked the imagination of a new generation of scientists. Still, this vision remained theoretical for some time. It wasn't until the 1990s that tangible progress began, as brilliant minds around the globe took meaningful steps toward realizing Feynman's dream. From legendary mathematical minds like Peter Shor to Einstein-era thinkers who laid the groundwork, several pivotal figures contributed to this unfolding quantum saga. A major breakthrough arrived in 1994 when Peter Shor introduced a quantum algorithm so profoundly disruptive that it sent shock waves across the scientific community. This ingenious formula demonstrated that quantum computers could be used to unravel complex cryptographic systems and accomplish computational feats that no classical machine could replicate. Shor's work marked a turning point, igniting a surge of interest in building practical quantum devices. It took nearly another decade, but finally, the first hands-on quantum computers began to emerge. Though rudimentary, they represented the first tangible steps toward a technological revolution. Among the early pioneers was Isaac Chuang, who, in 1998, collaborated with Neil Gershenfeld of MIT and Mark Cuban from the University of California to construct a basic 2-qubit quantum computer. This experimental model, developed at Los Alamos National Laboratory, demonstrated the core principles of quantum computation in action. Still, in the grand scheme of things, this early prototype offered little practical use. It wasn't capable of addressing the pressing scientific challenges of the time. The most limiting factor was its scale. The system only included 2 qubits. In quantum computing, a qubit, or quantum bit, is the fundamental unit used for storing and processing information. The computational power of a quantum system increases exponentially with the number of qubits it contains. To put it in perspective, a 2-qubit device is virtually insignificant when compared to the immense potential of a 10,000-qubit quantum supercomputer. Yet, the true marvel of quantum computing doesn't rest solely in the number of qubits a system possesses. It lies in the extraordinary characteristics of the qubits themselves. Unlike classical bits, which exist strictly as ones or zeros, qubits possess the remarkable ability to exist in multiple states at once, a quantum property known as superposition. To illustrate, a classical bit is either 0 or 1, no exceptions. A qubit, however, can represent both 0 and 1 simultaneously. This astonishing feature allows qubits to adapt to various conditions in real time, fundamentally altering how data is represented and processed. Superposition is one of the quantum world's greatest gifts, one that has sparked intense excitement and curiosity among physicists and computer scientists alike. Thanks to this ability, quantum computers can perform calculations and solve problems at speeds and scales that defy comprehension, dwarfing anything that classical computing can offer. Another key component in the structure of a quantum computer is the set of quantum gates. These gates operate similarly to logic gates in classical computers, but are designed to manipulate qubit states in sophisticated ways, enabling the execution of quantum algorithms and specific problem-solving tasks. The elegance and complexity of these quantum gate operations are enough to leave even seasoned scientists in awe. The year 2001 marked another major milestone for the quantum community. That year, researchers at IBM successfully employed nuclear magnetic resonance, NMR, to control the states of qubits, a technique that represented a huge step forward in manipulating quantum systems with precision. It was a moment that energized the field and opened new doors for the future of computing. The initial flawless implementation of Shor's algorithm marked a pivotal moment in the realm of quantum computing. It didn't just leave scientists in awe. It ignited a wave of inspiration that pushed researchers to dive even deeper into the possibilities of quantum technology. With newfound momentum, the scientific community began rapidly advancing quantum systems, consistently developing increasingly sophisticated quantum machines. The number of qubits housed within these devices began to grow exponentially, thereby unlocking the ability to conduct increasingly complex computations that classical computers could not manage. By the year 2010, a remarkable stride was made in the quantum frontier when a team of researchers from the University of Science and Technology of China achieved a feat long thought to be confined to the realm of science fiction: quantum teleportation. This bewildering yet revolutionary phenomenon involves transferring a quantum state of a particle from one location to another without the particle itself traveling through physical space. The Chinese scientists successfully transported quantum state information across distances as far as 10 meters, a notable milestone that proved quantum data could be transmitted over relatively large spans. This success laid the groundwork for a future where quantum communication networks that may one day replace our current internet, could become reality. Just 3 years later, in 2013, an extraordinary collaborative project was launched, one that would become the most ambitious quantum initiative up to that point. In an unprecedented alliance, Google and NASA partnered to introduce a groundbreaking technological marvel known as the D-Wave quantum computer. This formidable machine was stationed at NASA's Ames Research Center and was envisioned as a tool with endless potential, from exploring alien planets to revolutionizing the way search engines interpret and process information. The scope of its applications seemed boundless. At the time, Hartmut Neven, the director of engineering at Google, offered a visionary perspective on the promise of D-Wave 2. He remarked that quantum computing could provide answers to the most intricate challenges in computer science, particularly in the field of machine learning. Machine learning, as he elaborated, depends on constructing accurate models of the real world to forecast outcomes with precision. Whether the goal is to discover cures for diseases, formulate sustainable environmental policies, or enhance search engine algorithms to understand natural speech and online content, more accurate models are the key to advancement. Quantum systems, Nevin suggested, might be the missing link in making those models a reality. And indeed, the D-Wave 2 appeared to push the boundaries of possibility. It performed optimization tasks at a rate up to 10,000 times faster than conventional computers and showed promise in solving intricate machine learning challenges that would leave classical systems floundering. The revolutionary capabilities of this quantum device filled experts with the belief that its potential had barely been tapped and that its possibilities extended even into the cosmic unknown. Within certain sectors of NASA and the scientific community, speculation began to rise that such a system might even help confirm the existence of extraterrestrial life. This idea stemmed from a compelling new theory circulating among astrophysicists and cosmologists, the concept that quantum computers and black holes may be fundamentally linked in ways we are only beginning to understand. In the realm of quantum mechanics, black holes are believed to be the ultimate containers of quantum information. This understanding has led to provocative ideas suggesting that intelligent alien civilizations could be using black holes as natural quantum computers. These bold theories go a long way in explaining the enduring mysteries surrounding black holes and why we have yet to encounter concrete signs of alien civilizations. According to these ideas, it's not that extraterrestrial beings don't exist, but rather that their methods and technologies are so advanced that they lie beyond our current detection capabilities. Some astronomers posit that if we could engineer quantum computers that mimic or interface with black hole mechanics, locating alien civilizations might become trivial. The development of the D-Wave machine, therefore, was perceived by many as a potential stepping stone towards such discoveries. Unfortunately, these ambitious aspirations were brought to a halt when the government made the decision to shut down the D-Wave project. The decision, though disappointing to many, was driven by valid concerns within the scientific and intelligence communities. Specifically, the fear that quantum computers might be exploited for cyber attacks or unethical purposes. You see, quantum machines are so advanced that they can theoretically bypass modern encryption systems with ease. Cryptographic algorithms, the mathematical backbone of data encryption and digital privacy, rely on complex equations that are currently unbreakable by traditional computers. These algorithms scramble plaintext data, rendering it unreadable without a corresponding decryption key, thus ensuring secure digital communication and data privacy. But quantum computers threaten to upend this balance. For example, cracking the combination to a high-security safe, one that might guard millions of dollars, would take traditional computers years, if not centuries. A quantum computer, however, could decode the encryption and open the safe in mere seconds. This unsettling possibility naturally raised red flags. What would happen if this immense power were to fall into the wrong hands? Though NASA was compelled to pause its use of quantum systems like D-Wave in the search for alien intelligence, Google continued its quest for quantum excellence. The company doubled down on its efforts and achieved a monumental breakthrough in 2019, a milestone known as quantum supremacy. This groundbreaking accomplishment was made possible by Google's extraordinarily powerful quantum processor named Sycamore. The concept of quantum supremacy refers to the moment when a quantum computer is able to solve a problem that no classical computer could solve in a reasonable amount of time, or perhaps not even at all. Sycamore's processor tackled such a problem, one that would have taken the world's most powerful supercomputers millions of years to compute, and solved it in mere seconds. The implications were mind-blowing, turning heads across both the scientific and technological communities and expanding public awareness of quantum computing's potential. Then, in 2020, tech giant IBM made a major return to the spotlight with the introduction of its IBM Q system, the world's first fully integrated quantum computer developed specifically for commercial applications. Unlike all previous quantum machines, which were limited to academic research or government use, the IBM Q was designed to be accessible to private enterprises and even individuals. This democratization of quantum technology marked the dawn of a new era, one in which businesses and innovators could experiment with quantum systems on their own terms. The emergence of commercial quantum computers also meant that scientific agencies like NASA could finally resume their exploration of alien intelligence. The Fermi paradox addresses the contradiction between the statistical likelihood of alien civilizations in our vast galaxy and the stark absence of any observable evidence of such beings. In theory, if advanced life forms were truly out there, and especially if some had developed spacefaring capabilities, they should have left behind detectable signs, artifacts, or signals. And yet, we have found none. But what if our inability to detect alien civilizations doesn't stem from their absence, but from the limitations of our own tools? What if intelligent extraterrestrial life is operating on a level so advanced, using technologies that completely evade detection by today's instruments? Perhaps only with next-gen quantum devices, machines of almost unimaginable power, can we begin to uncover the truth. This provocative idea is now gaining serious traction among leading thinkers in physics and astronomy. Renowned experts such as Dr. Michio Kaku have entered the conversation, lending their voices to the growing belief that quantum computing could be the missing piece in our search for intelligent life beyond Earth. In today's pursuit of advanced cosmic detection, scientists are branching out from conventional tools and exploring extraordinary techniques, ranging from detecting high-energy particles like neutrinos to experimenting with the potential of quantum-based communication networks. In a riveting interview, theoretical physicist Michio Kaku offered a jaw-dropping hypothesis. The universe might be threaded with a concealed interstellar superhighway engineered by extraterrestrial civilizations. According to Kaku, this clandestine system could be enabling an endless number of alien entities to traverse the vastness of space undetected. This astonishing possibility may provide the missing link in our long-standing puzzle of alien silence. Yet, our present-day technological thresholds remain insufficient to investigate such a concept thoroughly. For decades, the scientific community has mostly relied on monitoring radio waves emanating from distant stars, clinging to the hope that alien civilizations might be broadcasting their presence. But this narrow methodology could be significantly limiting our chances of discovering extraterrestrial life forms. Perhaps when the immense processing capabilities of quantum computers are fully unlocked, we'll finally possess the means to detect and explore this elusive intergalactic network that Kaku alludes to. At present, quantum computing remains an emerging force recognized for performing mind-bending tasks such as high-level simulations, deep learning enhancements, and intricate optimization solutions. However, the full promise of quantum computation is still out of reach. Until physicists develop more robust control over quantum bits or qubits, the basic unit of quantum information, we may never fully witness the extraordinary capabilities these machines are meant to offer. One of the most remarkable features of quantum computing that has captured the imagination of scientists is the phenomenon known as quantum entanglement. This is a condition where particles become so interconnected that the state of one instantly affects the other, regardless of how far apart they are, whether across a lab or across galaxies. This mysterious interdependence means that qubits can influence one another even if they are separated by light years, a phenomenon Albert Einstein famously dubbed spooky action at a distance. This interconnectedness allows qubits to work collectively, processing immense amounts of data in tandem. It's this capability that gives quantum computers their almost supernatural speed in deciphering encrypted systems or solving deeply complex mathematical puzzles in mere moments. Some industry leaders and technologists speculate that within just 5 years, quantum computing could upend the entire encryption paradigm we rely on today. Now you might be asking yourself, should we feel concerned about this? Isn't there a real danger that quantum computers could fall into the wrong hands, enabling a surge in cyber attacks or catastrophic breaches in digital security? Fortunately, the tech world is already a few steps ahead. Researchers and cryptographers are hard at work developing what's known as quantum-resistant encryption methods, ultra-secure algorithms capable of defending against quantum-powered hacking techniques. Think of these next-gen codes as fortified digital fortresses designed to be impervious to even the most sophisticated computational attacks. These cryptographic defenses are engineered to go far beyond the boundaries of today's encryption standards, promising to protect sensitive data and uphold the integrity of critical infrastructure well into the quantum future. But the usefulness of quantum computing stretches far beyond cybersecurity. Its ability to simulate atoms and complex molecules offers groundbreaking potential in fields like pharmaceuticals, material science, and AI development. Imagine being able to design advanced medications by simulating their behavior at the atomic level before ever testing them in a lab. In the financial sector, quantum systems are being trained to analyze staggering volumes of market data, detect vulnerabilities in complex systems, and even optimize investment strategies with a precision that traditional supercomputers can't replicate. These machines could simulate financial ecosystems in real time, forecasting market behavior and preparing institutions for all possible economic scenarios. Despite this promise, the road to quantum supremacy is filled with daunting hurdles. Technical incompatibilities, astronomical costs, and a scarcity of experts with the right quantum skill sets continue to slow down development. Building a working quantum computer isn't like building a better laptop. It requires rethinking hardware engineering and even the fundamental principles of programming. Every stage demands meticulous calculations, long-term planning, and trial-and-error refinements. Until we overcome these formidable obstacles, quantum computing's grandest potential will remain just beyond our grasp. It's in this context that Michio Kaku envisions a future breakthrough of historic proportions, one that could transform human understanding itself. According to Kaku, once we fully harness the synergy of AI and quantum computation, we'll enter an entirely new epoch of scientific evolution. At that point, our machines may become capable of making discoveries far beyond human comprehension, accelerating progress at a rate we've never seen before. Some futurists argue that this revolutionary pairing might not just push us forward, it could completely reshape civilization. But standing beside quantum computing in this technological renaissance is another formidable force: artificial intelligence. With the right fuel, AI could evolve into something far more powerful than any system we've ever built. Many thought leaders believe that the combination of AI and quantum computing will mark the dawn of a brand new digital age. Kaku himself has warned that the moment these two titans intersect, software fueled by revolutionary intelligence and hardware running on the principles of quantum physics, we could witness the birth of machines with unfathomable capabilities. While artificial intelligence is highly proficient at absorbing, generating, and replicating vast volumes of data, it still falls short when it comes to discerning truth from falsehood. Misinformation often slips through the cracks, and AI models can easily be manipulated into producing inaccurate or biased content. But by incorporating quantum computing into this process, the rules of the game could change entirely. The combination of quantum entanglement, superposition, and probabilistic inference could allow for ultra-precise data filtering, turning AI into a tool that not only understands content, but can verify it at a fundamental level. With these capabilities, computational accuracy would leap dramatically. The integrity of digital information would be ensured to an unprecedented degree. Imagine AI systems backed by quantum power. Not only would they respond to queries with astonishing precision and speed, but they might also possess the analytical foresight to anticipate human needs or even predict future events. These would be machines not just reacting to data, but actively interpreting and forecasting with quantum-enhanced cognition.